It is the silent guardian of every electrical system, from your home to massive industrial grids. The circuit breaker is the front line of electrical safety. Unlike a single-use fuse, the breaker is an automatic, resettable switch designed to instantly interrupt power during two deadly scenarios: overload and short circuit. Inside its tough polymer casing, the breaker houses an incredible fusion of thermal, magnetic, and mechanical components that detect and extinguish electrical faults. The entire mechanism is centered around the two main contacts, the fixed contact and the moving contact. When closed, they allow current to flow normally. The core challenge is detection. The breaker uses two distinct sensors, operating on fundamental physics, to monitor the current passing through. The first defense is against overload, when current slightly exceeds the safe limit for an extended period, leading to overheating. The second defense is short circuit and instantaneous. Massive surge of current caused by a fault, which must be interrupted in milliseconds. Let's explore the dual trip mechanisms that make the circuit breaker the most reliable protective device in electrical engineering. Protection against overload is handled by the thermal mechanism, specifically a component known as the bimetallic strip. The strip is made of two different metals bonded together, each expanding at a different rate when subjected to heat. Under a sustained overload condition, the excessive current causes the strip to heat up slowly. The metal with the higher expansion rate forces the strip to bend. This bending action activates the trip mechanism, a precise latch system that holds the main contacts shut. Once the latch is released, powerful internal springs instantly pull the moving contact away from the fixed contact, interrupting the electrical circuit. This action is intentionally delayed, taking seconds or even minutes, to allow for temporary, safe current spikes, such as motor starting inrush current. The thermal trip ensures that the long-term integrity of the cable insulation is protected from heat damage due to persistent overcurrent. For a deadly short circuit where current surges by thousands of amperes, protection must be instantaneous. This is the job of the magnetic mechanism. The current passes directly through a tightly wound solenoid coil. Under normal conditions, the magnetic field is negligible. But when a short circuit occurs, the current instantly jumps, creating a tremendously powerful magnetic field that operates on the electromagnetic principle. This magnetic force instantly pulls on an adjacent magnetic plunger or armature. This is a purely physical, high-speed trip action. The movement of the plunger bypasses the slow thermal mechanism and directly strikes the trip latch, causing the main contacts to open in less than 1 cycle milliseconds. The magnetic trip is purely amplitude dependent. Once the current exceeds the instantaneous trip rating, the breaker trips, regardless of how long the fault lasts. This speed is vital for protecting sensitive electronics and preventing fire or explosion caused by the incredibly destructive force of a high-level fault current. When the contacts rapidly separate under load, the high voltage attempts to jump the gap, creating a superheated plasma known as the arc. The longer this arc persists, the more damage it causes to the contacts. The breaker must extinguish the arc in the shortest possible time. The secret is the arc shooter structure of parallel metal plates. Magnetic forces drive the arc into these plates. As the arc is forced into the chute, it is rapidly cooled, elongated, and effectively split into many smaller, less powerful arcs, quenching the plasma instantly. This brilliant design protects every component of our electrical world. The circuit breaker is the cornerstone of a safe, modern power grid. If this 3D exploration of the circuit breaker's mechanical genius intrigued you, please hit the like button and share this with your engineering friends.
Subscribe to UA Electric for more essential 3D breakdowns of the complex systems that power our modern world.